A very good morning to the distinguished gathering here today, and I warmly welcome you all on behalf of the Department of Civil Engineering of the University of Moratuwa. I'm Dhiranjali Thoradaniya, the co-host of today's proceedings.
And I'm Dineth Vijayasekarak. From its inception, the Department of Civil Engineering of University of Moratuwa has grown rapidly and risen to the present state. Being one of the strongest and most well-accomplished academic divisions in the Sri Lankan university system, it operates under 6 divisions with the flagship undergraduate program and several postgraduate programs and research programs. In the sacrosanct field of civil engineering, groundbreaking research is an everyday phenomenon. Undergraduates and postgraduates of the Department of Civil Engineering undergo various research which often lead to innovative findings and pioneering techniques in the field. Hence, Civil Engineering Research Symposium is a platform for the undergraduate and postgraduate students to showcase their latest and novel research activities undertaken. Ladies and gentlemen, let us begin the proceedings of Civil Engineering Research Symposium 2022. To start off, let me invite the keynote speaker, Professor Campbell Middleton, and the head of the Department of Civil Engineering and Civil Engineering Research Symposium 2022 co-chair, Professor Chinta Jayasinghe, and Symposium co-chair, Professor Jagat Manatunga, to the head table.
The Department of Civil Engineering is a trailblazing department and an eminent field in the university. Touching the peaks of success would not be transpired without an inspiring leader. Being the pillar of strength to the Department of Civil Engineering, she has guided us to the current state of prosperity and growth. And that wonderful leadership is none other than Professor Chinta Jayasinghe, the head of the Department of Civil Engineering of the University of Moratuwa. Dear Madam, this invitation is for you to welcome the gathering in this gracious occasion. Very good morning, everybody. Conference co-chair, our keynote speaker today, and the chief guest, Professor Campbell Middleton, other distinguished guests, academic staff, non-academic staff, and my dear students. It is with great pleasure that I welcome all of you to the Civil Engineering Research Symposium 2022. A warm welcome to our keynote speaker today, Professor Campbell Middleton from University of Cambridge, United Kingdom. I would also like to welcome all academic staff, non-academic staff, all the presenters, all other undergraduate and postgraduate students. A warm welcome to you all. As we all know, civil engineers face many challenges due to diversity in the domain and its multifaceted nature. In order to keep up with state-of-the-art technology, together with resource limitations, some degree of out-of-the-box knowledge is essential. This symposium has been organized with the intention of grounding young engineers to face such challenges with the outcomes of the multifaceted research carried out both at undergraduate and postgraduate levels of Department of Civil Engineering. The wealth of knowledge that the academic staff of the department possesses would trickle down to the students in the form of final year research of undergraduates and at the postgraduate level. So this symposium creates an ideal platform for them to showcase their research outputs to a wider audience. Furthermore, CERS 2022 could be identified as a unique symposium since an eminent professor from University of Cambridge, United Kingdom, Professor Campbell Middleton, delivers the keynote address. I'm sure this would allow our students to get a flavor of state-of-the-art research going on in the developed world. Thank you very much, sir. Another unique feature of CERS 2022 is that the symposium is dedicated for one of our own eminent professors who retired in 2022. Professor Anuruddha Pussebala is our former Dean, Faculty of Engineering, for a period of 6 years. Also, the alumni batch intake 2004, who came forward to sponsor the symposium with their generous support, has made this symposium a landmark. I wish the CERS 2022 will be a fruitful symposium for all the participants, and it will benefit the civil engineering industry as a whole. I'm confident that the research findings presented can be used to address unsolved research questions with greater confidence. Thank you very much.
Thank you, Madam. You're truly an inspiration for all of us, and we are forever grateful for your support and encouragement.
Ladies and gentlemen, we are now moving on to one of the most anticipated items to today's agenda. It is the keynote address of Civil Engineering Research Symposium 2022 by Professor Campbell Middleton on the topic, Data is the New Gold. To introduce our keynote speaker of the day, I cordially invite Ishan Jaisinghe on stage. Professor Ishan Jaisinghe is a senior professor attached to the Structural Division, the Department of Civil Engineering, University of Moratuwa. Dear sir, this is over to you.
Good morning, ladies and gentlemen, the co-chairs, Professor Campbell Middleton, and all the others in the audience. Thank you very much for giving me an opportunity to introduce one of my good friends, Professor Campbell Middleton. So I first met him in Cambridge in 1989, April, in one of the functions held in the evening. And I saw a new face, a person who is talking a lot. And I was wondering who he is. And that day I learned we have got another research student to read for PhD. And he came from the industry. And first he had the experience working as a design and construction engineer in Tasmania, Australia. And then he came to London, and he worked at one of the key consultancy firms, or Arup and Partners, for a few years. And so one day he was at a party, and he met one of these British ladies. Asked, why you are here? And he said, I'm from, she said, you are from Australia, and why you are here? And he said, I have been asked to do an assignment in a third world country, so they send me here. Right. So he finished his PhD on some reliability analysis, and he developed a program for determining the strength of concrete slabs using both upper bound theory and lower bound theory. Is one of the landmark findings. And then he has also developed a computer program based on that can analyze any shape, a slab of any shape, subjected to any kind of loading. And somewhere in 1994, he joined the Department of Engineering, or Engineering Department of Cambridge University, as a lecturer, and then he rose to the post of Professor of Construction Engineering. And not only that, he was instrumental in getting a huge amount of funding from the industry. And the company that funded the funding is one of the key construction companies in the UK called Lane O'Rourke. So it's a big company, and they gave a huge amount of funding to set up a center to study about the construction and how to improve the construction technology. So lot of work, very novel work is happening in this center with 10 million British pounds funding over 10 years, and now they have approved another 10 million funds for another 10 years. So it's going to be a 20-year project. Initially, it was a 10-year project. And so there's a center where a lot of research is done. Not only that, there are research students, and one of our own lecturers, Dr. Kasum Karyasam, read for his PhD under the supervision of Professor Campbell Middleton, and at the moment, another engineer from Department of Civil Engineering, University of Moratuwa, Engineer Asita Ratnayaka, is also reading for his PhD under the supervision of Professor Campbell Middleton, and he said all these Sri Lankan students have been extremely bright, and he is very happy with them. So I'm sure. So the students in the audience also can show their colors if they work hard. So Professor Campbell Middleton has a great deal of experience, and he's going to share some of his experiences with us today. So I cordially invite Professor Campbell Middleton for his keynote address.
Thanks very much, Professor Titian, for the introduction, and Professor Chinta and co-chair for inviting me here today. And thank you to all of you. In particular, I've met a number of students during the week, as well as staff, and it's been a fantastic opportunity to see in person what you do here. And reiterating what Professor Titian, as he runs out with his mobile phone, said, I've been very fortunate to have several students from the University of Moratuwa come to Cambridge to work with me. And it's been an absolute delight, and they've done some very interesting work, some of which I'll mention today. So what I was hoping to do was just give you a little bit of an insight into some of the topical issues that we're looking at and discussing in the United Kingdom and also in much of Europe at the moment. And I've recently come back from a week in Australia as well, and there's a lot of overlap there. And try and give you some insight in just a couple of examples of technologies we've been using to great effect in civil engineering. And I'd welcome at any time, if any people have any questions, I believe we hopefully will have a bit of time. So to start with, the theme I've picked is the topic of, originally I was calling it data is the new oil. And that's a common expression reflecting in the 100 years ago how oil was the centre of so much of the economy and driving for wealth of the world. But now there's the conception that maybe data is the new oil. There's so much that can be derived from that. But it also opens up an interesting issue because the word oil is not popular at the moment. And certainly in Britain, you're not allowed to use the word oil. So you have to actually find some alternative. So I'm now going to call this lecture, Data is the New Gold. And if you see in the media, there are actually a lot of protests at the moment against oil companies all around the sustainability agenda, concerned about the future of our planet. So to start with, to introduce the talk, before I get onto the data, what I want to do is outline what the mission statement of the Langeroog Centre that I lead in the United Kingdom is, because I think it's a very good way of focusing all of us on what I believe is the most important issue we all face today, and that you in particular will face moving forward. So the mission of the Langeroog Centre in Cambridge is this: Our goal is to transform construction to improve the quality of life for all in a sustainable and equitable manner. And just think about that for a minute. Many mission statements, many government policies are all focused on improving GDP, creating wealth, creating money. But I would argue we as civil engineers have a responsibility higher than that. Our ultimate goal is just to improve the quality of life for everyone. And that's what civil engineers do. We create the built environment which improves that quality of life. But to do that, we must do it in a sustainable way and also in an equitable way. However, so the focus is on quality of life. But having said that, there's a big cloud on the horizon. And that cloud is climate change. And we've all seen the manifestations of that around the world. And hence that leads into a focus on net zero carbon. And carbon really is a proxy for equivalent greenhouse gas effect and covers all the greenhouse gases when we use the term carbon. So to start any lecture, and on the programs we do in Cambridge, I always ask lecturers to start with the following. Put up the United Nations Sustainable Development Goals and say to the audience, which of these do we address and are trying to focus on during the lecture? And I've blacked out those that are probably not so relevant, but you'll see quite a number of the 17 goals that are coloured reflect that the work we do impacts in different ways all of these things. And if you go through them, you'll see that we have such an important impact on society. Keep that in mind. Everything we do moving forward needs to be focused on how do we improve the threat to humanity in our world from climate change. And remember that you are the future. If you think carefully about the quantity of carbon generated in the world, depending on which measure you look at, it's anything from maybe 8 to 10% just comes from the built environment and construction industry, of which if you look at it, about a third is due to transport, about a third is due to energy generation, about a third comes from buildings. A lot of that around heating and cooling, particularly in Europe and places that where they need the cooling. And I'm delighted here that you don't need that so much with the lovely climate. So that's the background. What I'll do now is I want to go on and just bring a few comments about this concept of data is the new gold, because I think there are many misconceptions out there about what the value of this is. So let's think about data in the context of the buzzwords that you hear so often. We hear the word data analytics, big data, AI, artificial intelligence, machine learning, and they're thrown around very widely. And in fact, these days in research, you'll find nearly every research grant gets submitted to do whatever adds on the end, plus using AI and machine learning. Whether or not they do is a different question. So the question is, what are we going to do with that? And let's just think about artificial intelligence and machine learning. Now, we're all familiar with the massive technology conglomerates like Google, Amazon, Facebook, and Microsoft. And they've all managed to monetize the use of data, the use of your data, our data, in a way to generate enormous value in a broad range of activities. So one of the things we need to think about, how does that apply and benefit our society and our civil engineering? Now, I've got one example just of something in the areas of civil engineering, which I actually showed when I was here in 2015. And this is an interesting picture. It's actually by monitoring mobile phone IP addresses in London and just monitoring traffic for a number of stations. And if you monitor that and look at the density of the traffic, you end up getting what is a remarkably accurate map of the road network of London. And the density reflects the size of the road. So that abstract collection of phone data just suddenly gives you a really accurate map of the streets of London. So it's just one unique aspect, an example of how you can generate something of value by collecting dependent data here. It's interesting to note, of course, that it's illegal in the UK to use a mobile phone when you're driving. So I hope all those people are only passengers, not drivers. But anyway. But another issue which comes up in the use of data is the terminology, artificial intelligence, machine learning, and more recently the term deep learning. Now, this is a definition that I obtained from the web, just downloaded, of what some define artificial intelligence as, and machine learning. Let's just start off with artificial intelligence. They say it basically refers to programs with the ability to learn and reason like humans. Separate to that, the subset of that is machine learning, where we develop algorithms with the ability to learn without being explicitly programmed. That's the key bit. And then as a subset of that, more recently, they've developed what is termed deep learning, which is a phrase suggested by one of the leading academics in this field in Canada, which is really a subset in which artificial neural networks can adapt and learn from vast amounts of data. But the problem with these is they're being misused in my view. If you think about what artificial intelligence actually is, it's an attempt to mimic the power of the human brain. It's the attempt to take in, process, and make decisions by absorbing data to mimic the human brain. And I think most of the experts in the field contend that we're a long way from doing that. The brain is such an extraordinary organ, an extraordinary computer. It can process and handle things. And a very good example is computer vision. You can look at a group and extract information instantly with the most powerful computers and programs in the world struggle to do. So it's a very large area of research, and we have a lot going on. But too many people use the term artificial intelligence and pretend that we're approaching the ability to do that. There's some extraordinary examples of really clever developments. Companies like DeepMind, owned by Google, the academic Demis Hassabis, launched DeepMind and come up with things like the AlphaGo, and you've seen these computer programs playing chess, playing Go, and that great effect. But most of what we actually do is machine learning. It's taking large amounts of data and try and identify patterns, look at anomalies, and extract from that useful information and allow us to make predictions. So don't get drawn into this myth that we're approaching the ability to mimic the human brain. But having said that, it's a huge opportunity for the future, and there are many areas where machine learning is incredibly valuable. So the question for us is, how do we use these tools to provide value in civil engineering? And again, I think there's a mismatch here. There are some examples where we can collect large amounts of data, interpret and use it, but actually it's a real problem. But in practice, unless the data has some link to the label or we know what it is, it's very hard to make that value case. And I'll give you an example. Cancer detection. It's huge opportunities by getting thousands of images of MRI or X-rays or scans of cancer versus scans without cancer, and training up programs using machine learning to identify for new scans the likelihood of cancer. Enormous opportunity there. And there are many others where there's large amounts of data. But I'd contend we're really in the early stages of civil engineering. Okay, so what I'll go on now to do is look at some of the questions we might ask, some examples of where data, or we collect information to inform what we do. Now, I've put it in a context here. I happen to be a bridge engineer. That's my passion. I've spent most of my career building, designing, or doing research on them. So the questions I'm going to ask are related to if you were bridge engineers and the use of bridges. But what we do is exactly analogous and applicable to all forms of construction, buildings, dams, civil engineering infrastructure, but we'll do it in the context. So the first question is, what are the sort of questions that managers of structures are asking and that we want answers to? And here's some examples. When I turn to the owners, the actual managers, who have a responsibility for the bridge network or the road networks, the first thing they want to know is it safe? Is the structure safe? And then how safe it is. What's my margin of capacity or margin of safety above the loads that are actually running on it? How long will it remain safe? What's the life of the structure? And what actions, what maintenance, what repairs do I need to do to make sure it's kept safe? And finally, how do I generate value from the bridges? The bridges are there to generate value, to provide transport corridors. But it's interesting because if I then go and talk to someone else, like a bridge assessment engineer, an engineer that does the calculations to see, is a bridge safe? Perhaps the loading is going to go up, or it's deteriorated, or there's a problem. They will ask completely different questions. First of all, they'll say, well, what are the loads on my bridges? What are the sizes of the trucks? How many trucks are there? What actually is the loading on it? What is the response of the structure? You all do and learn how to do analysis. What actually happens in reality? What are the strains and stresses? And also, importantly, how does the condition of the structure change with time? We assume everything is new when we design a structure, but with time it deteriorates. So in fact, what we're really asking is, can we answer questions about how are our bridges performing? That's the goal. And what data, what information do we need to understand that? Well, it's interesting in the sector, bridges, if you go around the world and look at the condition of bridges, it's a bit of a sorry story. And I'm sure it's the same here as it is in most countries, but I've got an example for the United States where they have a national bridge inventory representing all the bridges in all 50 states and their condition. And if you look at this plot, what it tells you is the number of bridges on one side and total number of bridges in the country of different types, concrete, steel, pre-stressed, timber, and other forms. And importantly, what proportion of these total number are what they call structurally deficient. So they've been analysed, assessed by structural engineers and said they're not adequate to carry the loads they're intended to carry. So they're unsafe. So they need strengthening or repair. And the other lot are functionally obsolete, no longer suitable for what they were designed for. So they may be too narrow, might be the load capacity for what's needed, whatever. But actually, if you look at these numbers, it's huge percentage. Something like a couple of 100,000 bridges in America need work, need replacing, need strengthening. That translates into billions and billions and billions of dollars. If I translate that into rupees, it's a number with so many noughts you don't want to even think about it. Huge problem. It's true all over the world. The second interesting thing is to look at why do bridges fail? What are the causes of failure? And if you think about what you do in your design, in your analysis, and in your training, most of the focus is, will a bridge be strong enough under the live loading you read in the code? Particular traffic loading from trucks or in rail loading. Nearly all the focus is there. So do bridges that fail mainly fail due to overload? The answer is no. When you look throughout the world at the causes of failure of bridges, collapses, means, you'll see that there are a whole lot of different causes, from steel fatigue, fire, earthquake, deterioration. There's the loading, less than 10% fail due to loading. Down here is the big outlier. Over half the bridge failures recorded around the world are due to scour. So scour is the erosion of foundations due to flooding in heavy rain events, and you get a lot of those there. And I think this was probably prepared by Kasun, actually, the slide, and some of the others. So actually, we're doing a lot of work on analysis focused on overload, but actually, what are we doing to get answers about improving the scour, which is the biggest cause? But there are many other issues facing the bridge community, and one of them is the vehicle loads that we are now putting on our roads is much higher than it was when many of them were first designed. And this is an example of a particularly heavy load in the UK. But just since 1982, which for me is not that long ago, 40 years ago, the legal load limit, the size of trucks in the UK, was limited to 32.5 tonnes. If you move forward, it's changed and progressively got bigger and bigger over the last 4 years. And back in 2001, it went up to 44 tonnes. and there's pressure to go by that now. So there's pressure all the way to increase the loading, but the bridges were designed for lower loads. Secondly, there's the amount of trucks that are illegally overloaded. And this is a bit of a frightening video, but I thought you might like to see this. Big heavy truck going on an overpass, and there's a joint in here in Italy, 2016. And tragically, that driver was killed. And you see the vehicle there resting over the end. And there was what's called a half joint, little hinged, a little infill joint there that collapsed. But it was because a grossly overloaded vehicle was on the roads. Could we have warning of that? How would we have known about that? How could we have measured the load on the truck? How do we know what the capacity of the bridge is? There's another issue as well. When you design bridges, there's a code of practice that has a model of what they think the maximum loading that you're likely to get on the bridge is, and you design for that. How accurate is that? What actually happens on bridges? Hamburg in Germany, 2007, where there was a strike. And as a result, the police changed the use of the bridge. You'll see they put all the heavy, very heavy trucks together, back to back in 2 lanes. No bridge is ever designed for that sort of loading. So could that have risked the bridge falling down? Do we have, and the question is, do we have data on what the real loading on bridges is? And the answer is we don't. It's quite frightening how little information we have. And then I mentioned the issue of deterioration. That joint on the bridge that collapsed is what's called a half joint bridge, which is where you get a step and an infill beam gets dropped in here. This is one from Canada, from an inspection in 2004, where you can see there's some cracks and some problems there. Sadly, in 2007, that bridge collapsed and that joint failed. It came down and killed a number of people. And yet it was inspected not long before that, and yet no one picked it up. There was no mechanism for getting data and information to inform. Similarly, and quite scarily, you see the condition of that one. This is taken from the busiest motorway section in Europe, which is part of the M6 motorway in London, in England, near Birmingham. And that's the big complex interchange there. And this section here, close up, is a joint of these so-called half joints there. Now that's still there. We went up and expected that, and we have absolutely no idea what's really going on, how strong it is, and it's a real concern. So we don't actually know what a lot of our structures are doing. You design them, big factor of safety, you think they're okay. In practice, we actually never go back and check or know or measure both the loads or the actual stresses, condition and strain. So if you think about in design, what happens, we have, if you think of a load deflection plot for a structure, when you go and design it, you design for some so-called serviceability limit state, a safe level to represent what you'd expect in the way of day-to-day loading on a structure. But of course, we have a margin above that for the ultimate limit state, the limit state in which it will break, it will actually collapse. And we have factors of safety to allow for that. In practice, if you went and tested any of the structures we build and design, the vast majority of them, if you actually tested them for failure, would likely fail significantly above the ultimate load. Not all, but well-designed ones, ductile, normally have inherent reserves of strength. The problem we have is that what actually happens is we don't measure where they really operate. We have no idea where on those curves our structures are operating. So how do we try and find that out? You rely entirely on your designs, theoretical calculations. Very rarely, except in research, do people go back and check. So what do we do as a way of managing all our bridge stock? This applies to many other infrastructure. The vast majority of our infrastructure, all aspects of the transport network, are managed purely by visual inspection. You go out, like this one on a cherry picker, you get up there and you look at it and you say, does it look okay? Do I see any cracks? You don't actually measure what's going on, so you have no idea what's really going on inside or underneath. You have no idea how heavily stressed it is, and you don't actually know what the loads are. But we rely on this visual inspection. So one of the questions is, how effective is that in determining the condition of structures? Now, there was a really interesting study back in 2001 done by the Federal Highways in the United States by academic named Moore and a group of others on the reliability of visual inspection for highway bridges. And that document is freely downloaded on the web, 2 400-page documents. Any bridge engineer, it should be compulsory reading. This will give you a big shock. And I'll just give you a snapshot of some of the key results from this particular document. What they did is they got together 44 trained bridge inspectors that do the visual inspection throughout the US, and they had a small subset of a couple of bridges that had been inspected in detail by experts to determine what defects or problems were on the bridge. So they had a known situation with a number of bridges. Then they brought the inspectors that had said in, do a normal inspection as you would in practice and tell us what's wrong with the bridge. And this is what they found. For a number of different types of deficiency, the number of inspectors is the second column that inspected it. And the third column is how many of those inspectors identified the known defect. So the first one, paint system failure. So on a bridge, it may be painted steel beams or guardrails. They were reasonably good at seeing flaking off paint. You know, the paint wasn't everywhere, but even then, only 2/3 of them. A third of them didn't even see the paint flaking off. And as you go down, corrosion, clear visual evidence of corrosion, only a bit over half detected it. Then you get more serious, member distortion, so warping, potential local buckling, problems that could lead to significant failure. Only 10% noticed the problem. Fabrication error, something's in the wrong place or didn't fit or wasn't working properly. No one, 2%, they just didn't see it. And crack indication, the bridge with a great big crack in it, only 2% of it even picked it up during the inspection. And so on, a bolt defect. So I've got a bolted joint, some of the bolts are missing, and only a third of them pick it up. I find that terrifying. And it actually led in the UK to an introduction of a new program to try and improve the training. We have a certification system now to develop competency for bridge inspectors, because what we found is bridge inspectors often were untrained. So they're going out detecting whether a £100 million bridge that could kill lots of people is safe based on almost no training and this accuracy of inspection. It's a bit like going to your doctor to go and you're worried that you may be sick, and you go to the front counter and the secretary at the front desk does the diagnosis. Even that secretary thinks you may look a bit unwell, then calls the doctor in. That's the analogy. Interestingly, they asked the question, why do bridge inspectors not perform well? And there are a whole lot of interesting human factors that I'd certainly never thought about before, and you may not have. There are human factors like these people are employed to do a visual inspection where you rely on good eyesight to do it, and half of them had a poor eyesight, had never had an eye check, and were colourblind, so you couldn't see things like corrosion. Visual inspection, but you don't check they can see. Things like that. Fear of traffic. Well, often you're exposed to lots of fast traffic nearby, and you're scared, so you do it quickly, you don't look properly. Lack of training. And there are a whole lot of other things. You know, it's windy, cold, dark when you're doing it, so you don't do it properly. And as usual, managerial constraints. They're never given enough time or resources to do it properly. So it raises the question with structural monitoring issues. In other words, what data do we need to collect to understand the performance of our structures? First thing we've got to say, well, why should we measure? Well, I've tried to answer that, the problems of visual inspection current methods. Then it becomes, well, what do we measure? And then how do we measure it? This is an ongoing debate. And what happens is you find there's a disconnect between the researchers and the people looking at structural monitoring and the owners and the managers, because the people who, like researchers who think we should do structural monitoring, they look at things like, well, with the sensors, we can get lots of data, it's really valuable, we make these smart structures, tell us what's going on. But the owners think, well, this is going to take lots of time, I don't really see the value of this data, and it costs lots of money. So there's constantly a debate going on. Now, it's really interesting. We were involved in a project a number of years ago called the Walton Bridge over the River Thames, the main river in London. And this is a picture of the final bridge that ended up being built there. But at the time, when they were first planning it, we had a very progressive client, a local council, who was really interested in getting structural monitoring, so get information about his new bridge. We had a designer who was at the cutting edge and really wanted to put in structural monitoring to be able to understand the performance of his structure. We had a good contractor who was interested in doing it as well, so he understood what was being built. And we were involved as researchers. We sat down and said, here we are, we've got a new bridge, we've got an enthusiastic team of people delivering it. What are we going to measure? What sensors will we put on? We spent an afternoon together and we really struggled. And by the end of it, we said, actually, we can't justify this, and we did nothing. Now, that led me to a lot of earnest consideration of what is the value of monitoring. And the net effect is that we've had a number of PhDs and projects since then asking that question, coming up with some answers, which I think do answer the question. And I'll show you where they're presented. And in fact, some of the work that Kasson was involved as part of it. But the bottom line is, if you think about it, most structural monitoring is done in response to a problem, where a client says, I've got a problem with my bridge, can you tell me what it is, or is the structure safe? And you go in and you put some sensors and you measure stress and strain or whatever after the fact. Rarely do we put sensors in the beginning to measure what is the performance, how does it compare with the actual design, and whether it's deteriorating. And the argument against doing that is, one, it costs a lot of money. Two, what you'll normally measure on most structures, it will be a big thermometer. All you measure is change in effects from temperature for the next 50 years. Because if it's designed well and it's built well, you shouldn't have any problems. It should be fine. But the evidence from the data is that there are a lot of structures that don't perform well, that don't perform as expected. And there's a lot of uncertainty. And the other question is, who pays for it? Does the client pay for it? Does the designer pay for it? Does the contractor pay for it? And who gets the benefit? If a consultant specifies a set of monitoring to go on a bridge, they don't want to pay for it. They don't get much benefit other than, well, they could get some benefit to improve their designs, but many of the designers don't want to get measurement because it might show they're wrong. If they were wrong, they'll get sued. Similarly, the contractors. So it's a really difficult question. Having said that, after a lot of thinking, we eventually put all our learning together and we published this book by the ICE, by some colleagues of mine. And we've tried to outline the answers to the question of why you should monitor and how you should monitor. And I would now contend that for most structures, and many structures, and certainly signature structures, we absolutely should be monitoring. And as a profession, we should be monitoring widely so we understand better how our structures perform, and we can modify our codes of practice and behaviour. And you'll see from some of the results that we can actually make substantial savings when we do that. So that's some background to the monitoring. What are the sort of big questions, though, that we should be answering that still face our profession? And I've put here a list of what I think are 5 holy grails, really difficult questions we need to try and get information about. The first one at the top is scale. Is the problem there? But the next one is reinforcing steel corrosion. We still cannot detect, predict reinforcing corrosion inside concrete structures. There's a huge industry trying to do it. And in fact, in Britain, just at the moment, I just got advised in an email this morning, the National Highway body had launched a program for what they call the moonshot, inappropriately, to try and find improved method of corrosion detection. Fatigue of steel and concrete. We still have very little data. There's historical theories behind it, but we don't actually measure it on our bridges. The ability to know the in situ strength of the actual strength of our materials, we can do sample testing, but the relation to the real strength, we use characteristic and tabulated strength. How different is that from the reality? And finally, the big unknown is loading. We just don't know what the loading is. Okay, what I want to do now then is, so I've tried to set the scene, make the case for why we need to do some monitoring and get data. And in the end, there's always the challenge that if we collect the data to make sure it's of value. And I've got here a couple of examples of bridges we've been working on over some years now. We first started in structural monitoring nearly 17 years ago and got into the use of fibre optics, but I'll talk about that. So a number of different aspects, one of which was actually the PhD work of Dr. Kasun. So I'm a bit nervous giving that, so you can correct me wherever he is. You're hiding. Tell me later if I get anything wrong. Right, let's start with fibre optic sensing. Now, this is a really interesting technology that we've been widely using, and it's quite widely used, particularly offshore oil industry and a number of sectors around the world. It's less widely used in heavy civil engineering, but we've been doing it for many years now, and I'll show you some examples. And the concept is that typical fibre optics optical fibres that you use your telecommunications, just the glass fibres, you use them to act like a nervous system in the body to detect what is going on in your structure. And there's some extraordinarily clever things you can do with it. And there are a number of different techniques. One of them that we've done a lot of work on, but there's actually only a very small number of groups in the world doing it, is called a very long name, Brilliant Optical Time Domain Reflectometry, BOTDR, and their variations of that. Basically what happens is you get a long fibre optic, you plug it into an analyzer, which is a very expensive, complex electro-optical device, and you stretch it out, stick it inside a beam, glue it onto a pipeline, stick it onto put it inside concrete structures. And what you do is you then, once it's inside, you send a light pulse, a laser pulse, along the fibre optic. And if at some point along the structure, it stretches, so it's strained, that will change the reflective characteristics of the optical fibre in a way that you get a reflection back. And by measuring that, you can actually quantify the degree of strain. Now, there are limitations of it. This particular technique is relatively slow, so it's only suitable for static applications. The gauge length that you can interpret, it's getting better all the time, but it's typically between about 200 and 500 millimetres. So it's an average strain, it's not a point strain. And there's some other limitations like that. However, you can do this over kilometres. You can literally put this along a kilometre-long pipeline and measure strain all the way along. That's being done in the oil industry and the water industry and others. And we've been putting these in a large number of tunnels, for example, wrapping them around tunnels. So it's one very interesting technique to measure strain, and you can also use it to measure temperature. The second technique, which is widely used and far more common, is what's called fibre gratings. And in these, a typical fibre optic, with lasers, you etch on little grating at fixed points along the fibre. So here are the little etchings. So it's like a mini strain gauge, a little grating that as that bit of fibre stretches, again, the reflective nature of the laser beam going on the beam can be interpreted, and you can measure very accurately to very, very fine strain readings what the strain is at that location. And this allows you to do dynamic readings as well, so it's quite widely used in bridges. So that's the technique. Now, here's some examples of where we've been using this. The first one in the top left is the big new train line underneath London called Crossrail. It's now been recently opened the Queen Elizabeth line, and that's a very large diameter. I think it's about a 40-metre diameter shaft down to one of the train lines, where we've been putting fibre optics in the wall to measure the strain during construction. The next one at the right was done by Laing O'Rourke, is a big new research centre in London called the Francis Crick Centre, where we've been putting it in the piles down in the foundations to measure the behaviour of piles. The bottom left is CERN, the Large Hadron Collider in Switzerland, where there's this large tunnel carrying the Large Hadron Collider, but there were some issues with the tunnel, so we're measuring cracks there. And then the other one is a huge redevelopment of a big train station in London. So what I'll do now is I'm going to just show some specific examples of the sort of information you get at. And this one is a bridge called Nine Wells Bridge, which is one in Cambridge. And here's the bridge, 3-span bridge, and that red line represents the main train line on the east coast of Britain from London north. It goes under here, and the bridge has large footings, large pile caps, and a large number of piles going down 22 metres. And the designer was very concerned that if these foundations moved at all, it could affect the train line, and that would have huge cost implications. So he was quite conservative in his design. And we put fibre optics in the piles and the beams. So here are the beams, and you can see the wires sticking out. We've got fibre optics running along that. And that was really interesting, because what we could do with that was we actually did it in the factory where they were built. We tracked through the whole process of manufacture, transport, erection, construction, and operation. And we could follow the losses experienced and the changes with time due to creep, shrinkage, relaxation, all these things those that do pre-stress concrete learn, and we could plot them. And these are the results for these particular beams that have fibre optics along them. These graphs are the amount of loss of pre-stress with time, and the code, the theoretical calculation is this one down here, the amount you expect to happen. We'll be able to track the losses with time. Now, to my knowledge, I'm not aware of anyone else anywhere in the world that's done that for a real bridge like this. We've done it for several, so you can validate, check what the theoretical assumptions of the code were. Reassuringly, the codes weren't too bad, the Eurocodes weren't too bad, but again, it was something quite original, getting data with value that hadn't been got before. Far more interesting, though, were the piles. So with these many piles, we went in there and we put some fibre optics in the piles while they're being constructed. These are cast in situ board piles. There's a picture of the pile cap. You can see there's a lot of piles in each one. And what we've done is, when the cages were being produced, what we did is we tied fibre optic along the beams, and here you see in the cross section is both fibre optic ribbon and also temperature ribbon, so that we get temperature and strain in multiple locations around the bridge. And what was interesting was to find what was the actual load in those piles. Now, many of you will have designed piles, and we make all sorts of conservative assumptions. And we can go and do testing by putting a heavy weight on to see if it fails. Has anyone ever measured what the load in the piles in a real situation is? Well, this is certainly the first time I've ever been involved in that. It was quite interesting. So this is one of the data sets for the load in a pile, 22 metres long, measured with the fibre optic. And if you look at it, this is magnitude of load from 0. This is depth here to 22 metres. And this is a bit of noise as you go down. But at about 4 metres, there's some surface effects there with the soft soil. Basically, there's no load in the pile. So those piles, of which there are a very large number, aren't really doing anything. What's actually happening is that the load is being carried by the big pile cap as a spread footing. Now, if you looked at the number of piles in that structure, that's probably millions of pounds wasted because we were so over-conservative. So that's one example. Let's look at some other bridges. A few years ago, we had an opportunity to do 2 brand new rail bridges from Network Rail, the main rail operator, in a consortium in a place called Staffordshire, the middle of England, shown there in the red dot. It was a great chance to try some new bridges. The first one was a concrete bridge called Under Bridge 11, which is only 12 metres span, multiple Y-beams, as they call it, with infill concrete deck. What we did, that's a mock-up of the deck with all the fibre optics. So the blue shows some of the, we've got transverse and longitudinal, top and bottom of the beam, shown in this cross-section. We didn't do every beam, we did half the beams, one on the other side to look at symmetry, purely to save cost. The second bridge we did was a steel bridge nearby. This is what's called a steel half-through bridge. And in this one, again, two main steel beams, transverse steel beams, and a composite concrete deck. And the blue shows the fibre optics. We have 291 fibre brag ratings in that one, and we had a large number. How many was in the other one? I haven't got the number there. A similar number in the other one. And here's some pictures of them being built. The bridge itself, we put additional sensors on. These are accelerometers, laser detectors to measure the train wheels. And what we were doing is those lasers are there to monitor the position of the wheels. We use that because we're developing a load monitoring. The bridge was actually a weighbridge. And here's the sort of results we get. The graph in the top right shows the data real time coming through a train crossing. So what we're doing is we're able to measure real-time the strains in those members of the bridge. And our goal is to move forward with that and develop a digital twin to represent the data. So we take the data from the sensors into our database, visualise it. We have various analysis models for the weight of the bridge. We do some finite element of the stresses. And from that, we can work out estimates of the fatigue life, condition of the bridge, and all these questions I was asking earlier, and that can inform repair and maintenance decisions. So we end up with some models in which you can show the degree of stress in the fibres, and there's all sorts of ways you can plot that. But the most important thing was this. This is actually a plot of load, the weight, against distance along a train, and we're now able to accurately measure the axle loads on every single one of them. And again, to my knowledge, there have been attempts at this. This is the first time where I understand this is going to be a permanent installation for measuring the loads of bridges. And what comes out of it is the interesting thing. This again is a graph showing the maximum moment of the beam in the middle of one of the bridges versus the load caused by different trains. These are different types of train. These are freight trains up here, the heaviest loaded trains. And this is the moment generated by those different types of trains. So this is over a couple of years, tens of thousands of data points, everything that's gone over. That's the maximum load that was experienced moment there. The yellow is the characteristic value of what was expected in design. That's the serviceability limit. That's the ultimate limit. So in fact, on this bridge, you could have quadrupled the load and you'd still be under the serviceability limit. It's operating at around about 12 to 15% of the load. And the designer thought it was heavily stressed. That's a huge factor. Okay. Now look, I've only got a few minutes left. So what I'll do, seeing I've got the opportunities, I'll just quickly mention the work that Kasum did, just very briefly, because I think this is some of the most original work in this field that's being done anywhere in the world. So we'll just quickly look at scour. And so, as we said, it's a major problem around the world. That bridge is one from Ireland. The picture where a fully loaded commuter train went over it a couple of minutes before it collapsed without any warning. Could have been a catastrophe with hundreds of lives lost. And scour basically refers to the loss of material under a foundation due to erosion, due to the water movement, particularly in floods. And the problem is, at the moment, it's really hard to inspect hidden down underwater, and often they just send divers down to have a look and feel around, and prod around. And that's about the best you can do, but it's very dangerous and very expensive. And here's an example of what happens when you have floods. Fully loaded container vessel somehow or other got in the river, smashing up against a bridge. And there's a device that's been developed in the UK called the BridgeCat, which is basically a sonar on the end of like a crane arm, which goes underneath and generates sonar images of the cross section. So there we can see the piers, and this is all showing the eroded scour underneath that pier there. So they're worried about it. So what they needed to do was repair it. So the plan was to go in, this represents the scoured material. It's not all the way across, and they're going to fill that up and put a concrete capping on it. So it's a fantastic and unique opportunity to go in and measure the behaviour of the bridge while it was in a scoured condition. Then it was repaired, and we could then measure again afterwards, so you get a before and after. So that was quite a unique opportunity. And here's Kasun and his team and some of the operators measuring it up and putting the sensors on. And they ended up putting accelerometers, a vibration method, onto the piers and deck. And what he did was he measured the vibrational response of the structure, in particular the piers, without scour. You'll see 17.1 hertz. And then he did it again with scour. He did it with modelling. He did it for real on the full-scale structure, and he also built some moderns in the centrifuge. So really, he did 3 PhDs in one. It was quite extraordinary. But the clever bit was, in here, he analysed not just the vibrational modes, which is what most researchers around the world have done. He went one stage further and looked at the mean spectral density of the response over a 6-month period, and he found this trend when the scour started. It then was decreasing, and then when the scour was ended, it levelled off. So you got this distinct change. Now, no one else in the world has done that. And what he's shown is this technique for piled foundations, and at this stage it's only piled foundation, could be remotely used to monitor and give warning of scour. No one else in the world could do that. And we're very lucky but unlucky in that we were going to get the National Highways was going to set up £1 million contract to take Gaston's work forward, but then COVID came in and they'd actually awarded the contract and then they pulled the plug and then we've had COVID. So it's something, it's an opportunity to future. And I was in Australia last week and all the bridge owners there were really interested in that as well, Gaston, so you better pop down there and tell them. Really original work, and interestingly, the opportunity from a student point of view, Kasun came up with this idea to do vibration monitoring. And I was really reluctant because I've seen a lot of vibration monitoring around the world using what's called modal analysis. Most of it, in my opinion, makes very little sense. It doesn't actually give you the damage measurement you can. I was sceptical, but Kasun had done the homework. He was very keen to do it. To give him credit, we've gone forward, but he's done some really original work. So there's opportunities to still make a difference, do something new in a field where there's not much that's really novel, you could argue, but there are huge opportunities. There's one case where Kasun's done some unique, first in the world type stuff, the other sense of things, and there are many other areas. So I'd encourage you, be you finishing your degree and going on to do postgraduate work or going into industry, work closely with universities, look for opportunities, challenge the status quo, and you'll find that you'll be able to get data. So to conclude, in answer to the question, is data the new gold? I would argue yes. The challenge for us is to go out there and get it in a meaningful way to inform, to allow us to make decisions. Because data for the sake of data is a waste of money. It has to be there to inform decisions. And even if that decision is do nothing, it's still valuable. But the challenge is to think about what to measure, how to measure it, and to get that data meaningfully and not just collect data for the sake of it. So I'd encourage you to think about that and let's transform our industry going forward. Thank you very much. Oh, sorry. Yeah.
Thank you very much, dear sir. It was quite delightful and enthusiastic to listen to such an insightful delivery. First of all, I have to say that I was particularly over to see that how mobile phone IP addresses of the public represented the roadmap in London. So I think our audience got a very vast understanding about why data is actually the new gold and how the lack of data or knowledge is a frightening factor that can lead to multiple tragedies. Also, how can we forget the holy grail of structural health monitoring? So on behalf of Department of Civil Engineering, I sincerely thank you once again for providing us with a great opportunity to enhance our knowledge on cutting edge technologies and research. And there are many real world